Okay. So hi everybody, and welcome to the second part of our talk. And so Sergey gave an overview about fuzzing, what fuzzing is, and demonstrated some of the results that we had when fuzzing some automotive software. And now in this part, we will address some of the technical challenges of integrating fuzzing into the development process and show what we do in order to enable companies to integrate fuzzing. So I am Khalid, one of the co-founders of Code Intelligence. And so before Code Intelligence, my research was mainly focused on binary code analysis, developing tools to help analysts in reverse engineering binary code, and also worked as a malware analyst, developing and using both static and dynamic analysis techniques. And in our research projects, I worked closely with the industry, and one key observation kept appearing is that while analyzing security incidences and malware is quite important in order to understand what's happening and developing countermeasures, but finding the vulnerabilities and fixing the vulnerabilities that enable these incidents to happen in the first place is even more important. And therefore, we decided to start Code Intelligence with the vision of enabling companies to easily integrate fuzzing into their development process. And in this talk, we'll go through 3 use cases, practical use cases, in a project that we did for automotive software and or embedded software, and show how we enabled these in this case, how we enabled the companies to integrate fuzzing. So so let's meet Max. So this is the first use case. Let's meet Max. He manages a relatively large software development team and wants to integrate fuzzing as soon as possible. And however, they have a really strict deadlines regarding their feature roadmap. And while their team, they have really great engineers, but they don't have a deep experience in fuzzing. And so basically they have several challenges when they want to integrate fuzzing themselves into the development process. So the first part is continuous integration in CI/CD. So as Sergey mentioned, the earlier you find a bug, the easier it is to fix, and the less costly it would be. And this means that fuzzing, the software should be fuzzed continuously with each change to the code. And you need to be able to easily analyze and understand the fuzzing results and act upon it. And the second challenge is the manual changes that you have to do into your build system. So we just seen as in Sergey's talk, for coverage guided fuzzing, you need to instrument the code, and to do this, you need to use some special compilers and some special compiler flags. And basically, what this means is that you need to change your build system to use these kind of compiler and compiler options. And this proves to be one of the largest roadblocks preventing companies to integrate fuzzing. In large projects, you partly have different build systems for different components. In some cases, you have the compiler hard-coded into the build script, which makes it less configurable. So you have to be aware of these options and changes that you need to do in order to have effective fuzzing. And so the last step is you have to create the fuzz test. So you have to create a test harness that would take the input from the fuzzer. It would act as a bridge between the fuzzer and your software. And while with open source fuzzers and fuzzing engines, you have to address these challenges by yourself manually. And let's see how these challenges, how we address these challenges and help developers integrate fuzzing to their development process, making fuzzing more acceptable for both management and developers. So here we see sort of the complete workflow that you need to do when you integrate fuzzing in CI/CD, in the development process. So you start with an initial setup, you create the fuzz tests, and with each change to the code, fuzzing is triggered in a continuous integration where you instrument the code, you fuzz the code, you see the reports, and then the bugs that the fuzzer found. Based on that, you fix them, and basically you redo this loop again, you fuzz again, and you do it in order to check that your fixes actually corrected the mistakes. And so we'll have a look at each of these steps in more details. So in this case, let's start from the end goal. So what to do when fuzzing finds a bug? So what we want to do is actually be able to easily understand what went wrong and fix the bug. And the great advantage of fuzzing is that it provides a proof for each finding, meaning that it provides a concrete input that triggers and reproduces the bug. And so this means that as a developer, you can simply analyze this bug in a debugger. And so CI Fuzz enables developer to start the debugging session in their IDE directly from the CI/CD pipeline with few clicks. And let's see how this looks in action. So here we see this is Tint, a library for encoding and decoding barcode that's used in a lot of embedded software. And we analyze this library as part of analyzing a larger car sharing application. And here we set up fuzzing for this project in GitHub using GitHub Actions so that fuzzing is triggered on each pull request. So let's have a look at the pull requests here. We see that this one has failed. So we can click here to get more details. And we see, okay, that we got from CI Fuzz that it found a Stack Overflow for this test. And you also get, as a part of the report, a code coverage report to show what code coverage has been achieved by this test. And here you see view finding. So you can click here, and this will take you to the CI Fuzz platform where you can have more detailed information about the bug. So I click here now, and now I see in the CI Fuzz platform you see a more detailed explanation about what happened. But now, if I want to debug this bug, I can click here on debug in VS Code, and this would basically start a fuzzing session in my IDE for this test using the crashing input that the fuzzer has found. And in a debugging session, I can easily have a look at what went wrong. So let's do that now. Exactly. So now I'm inside VS Code. It's an IDE, and the application is started with the crashing input. Breakpoints here were automatically set because from the fuzzer we get the stack trace, and based on that we create the breakpoints automatically. And here you can see the concrete input that the crashing input that the fuzzer has found. And now I can, as a normal debugging session, I can click through the code and observe at each location all the local variables and all the values. And this gives me it's really easy to understand what happens in the code. Okay, so this is debugging. So we saw how we can, with a few clicks, move from start a debugging session from the CI/CD. And here we saw an example with GitHub, but the solution is CI agnostic, meaning that it works with any continuous integration like Jenkins or GitLab. And we also saw roughly how the report looks like. And this takes us to the previous step. So having a look at the fuzzing report. So having a look at an overview about what bugs have been found in this fuzzing run, and being able to filter for some results to print some reports. So let's have a look at how this looks in the A-Util platform. So here I'm now in exactly it's the web app, and I can show the fuzzing results of all runs. So here I have an overview about all errors or bugs that have been found by fuzzing. You can have several filtering capabilities by language, by severity, or by bug type. One can also print a report if this is needed by management, for example. And so now we saw how the report looks like, but in order to find to have a report of the bugs, we need to fuzz first. So this takes us to the previous step. And here, in order to have an effective fuzzing run or effective fuzzing, we perform what we call ensemble fuzzing, meaning that we combine several strategies at the same time. Like there are several fuzzing engines, several strategies to find new inputs that maximize the code coverage, and we use these collaboratively so that if a fuzzing engine if one run finds an interesting input, this will be shared by all other runs. And so in the platform, you can scale fuzzing runs, and we take care of all of the fuzzer orchestration, and then you can also have you can easily monitor the results. And so and lately we introduced or we added a concurrent execution capability, meaning that we combine fuzzing and concurrent executions as being now the two most effective ways to, and this combination is proved to be really effective in finding bugs. And so let's see how this also looks in CI fuzz. So here I can see the different tests. I can have a look at our previous runs, and you can get the more detailed information about how, like, the fuzzing performance, how many executions per second did we have, how many inputs did the fuzzer find, and etc. So yeah, in order to perform, so we saw how fuzzing looks like in the platform, but in order to perform that, we need to instrument the code. And instrumentation means building the code in a way where we can add these markers to the code that can give us on the one hand the coverage information, and on the second hand integrating the bug detection capabilities. And as I just said, this, based on our experience, this is one of the largest roadblocks that prevented companies or developers from integrating fuzzing. And to address this issue, we built a software or a fuzzing-aware build interception framework, meaning that we run the original build system unchanged in a controlled environment, and before we monitor all compiler invocations at runtime. And before we allow a compiler invocation to execute, we perform all necessary changes on the fly, meaning that we can change the compiler, we can change the compiler options, we can add new flags, remove some options, and so we do all what's necessary in order to instrument the code automatically. And so this means that as a developer, you have really two advantages here. First, you don't have to change or touch your build system in order to set up fuzzing. And second, you don't have to be aware of these options, because in order to, our vision is that if you want, in order to set up fuzzing, to use fuzzing, you don't have to be a fuzzing expert to be able to do this automatically. And so, yeah, let's see how this would look like in action. So here I'm back to my IDE, and here, so this is basically the same project, and we have this the same test that we saw where we saw the bug, and now. And here in this project, we didn't touch the build system in any way. So now we're running the original build system, and all I have to do is I can click start, and this would automatically instrument the code. So this would automatically trigger our system to automatically instrument the code and start a fuzzing run. So this is what we will see right now. So I will click on start and to see that. Fuzzing the code is instrumented and fuzzing is started without having to do any manual changes. So now the code is being built, is instrumented. And now a fuzzing run is started. So, and this is with coverage guided fuzzing. So the code is instrumented. A fuzzing run is started automatically without having to change anything in the code. So now that we have seen how instrumentation can be done automatically, we go to the previous step, which is actually setting up fuzzing or creating a fuzz test. And so a fuzz test on the module level, on the unit test level, you can think of it as a similar to actual unit test, but instead of testing the API or the module with specific inputs as you would do in the unit test, you would take the input from the fuzzer. And for this, you need to create these tests. And this is also one of the main roadblockers for fuzzing adoption, because there you need to know the exact dependencies and for each the module that you want to test, and the exact compiler options that you need to compile this module. And we also automated most of this process, and I will see now how creating a fuzz test would look like in the platform. So here I can have a look at so here's the code. We see that it has some tests. I can have a look at one of the tests, and we see that this function does some encoding, and anything that has to do with parsing, encoding, decoding, it should be tested. And I can go here to the definition and see this annotation here. It's called fuzz this function, and here I can simply click on this annotation, and what this would do is it would automatically create a fuzz test for me. And we see here, so this is the source code. Here, all includes have been resolved automatically. And also, if we have a look here, all build flags have been automatically resolved, so you don't have to care about that. The system takes care of this automatically. And all what you need to do as a developer is taking this function and basically feeding the data that the fuzzer provides to your API, and that's it. You have a completely figured fuzzing test. And of course, here just an important thing to notice: it's we don't only support row buffers. You can basically provide other data types, like for example, if your API expects a C struct, you can here say I want to fuzz it, and my data is basically a struct. And what this would do is that the fuzzer would automatically generate valid C structs, and they will be mutated also in a meaningful way. So now we saw that how CI-fuzz automates most of the parts of creating fuzz tests, and so just how we're able to do that. The idea is that we're using for this part our build system interception framework, and here we build the code once in a setup step, and while building the code we keep track of all compiler invocations that happened, and based on that we build a sort of call it as a compiler compilation database where we keep track of all dependencies and all compiler invocations. Okay, so now with this we've seen a complete workflow from setup to create a fuzz test to instrument to fuzz, see the report, and fix the bug. And for most of the parts, everything was, or most of the stuff that you need to do was automated. And we started actually from the goal and went back to the setup step. And we'll show another example where we show you exactly what we did in order to test another software. Basically, see what we did there. And we'll have a look at A-Util. So A-Util is a library from Audi that we tested, and we found bugs there, and we created a pull request in order to fix these bugs. And they were really kind enough to give us permissions to show this in our demos. And here we'll show the complete workflow what we did in order to find the bug. And yeah, A-Util is a utility library that have utilities for builds, for systems, for regex, etc. So okay, so what we first we need to initialize the project, and yeah, we give. Since it's a CMake project, we automatically detect the build system and provide a proposal or a suggestion to the developer to use it. And if your projects need some special dependencies, you can provide a Docker image where you basically test the application, so that the image has all the dependencies that you need. And now I can say, okay, this is fine. I just initialize the project, and what this builds the project and builds the compilation database that we need for automating the creation of the fuzz target, of the fuzz test. So now it's initialized. Then I can basically, similar to what we did in the other projects, one test is testing the file system. It has a test for the path library to the toString function. I can click here to go to the definition, and again, I can see, I say, okay, fuzz this function. This basically creates a fuzz test automatically for me. And all I have to do now is basically feeding this data to the fuzz test. So what I can, so this is, here's the code that we configured. I just to save some time of copy of writing code, I can just copy that here. And so what I'm doing now is I'm taking, and so now it's complaining that it's not the correct type. I can change this is to a char byte, and now I'm creating a string, feeding and creating an object, and calling the toString method. And here, and now I'm all good to go. I can just say here, this is the test that I created. That's automatically configured, and here you see the build flags were automatically created. I can then now start the test. And this is familiar now. You just instrument the code and automatically then start the fuzz test. And now this is starting. And you see that it's already found, it was so quick to find the error. And I can here go to have a look at the error. And I can start debugging. Basically, it's very similar to what we saw in the previous example. And here you just you see this variable that is used as an array index, and we see that here in each iteration it's decreased by 2. At some point we have it here as 0, and 0 minus 1 is minus 1. But when it's interpreted as an unsigned integer, it means that it's a very high number. And then we're reading from a memory location that we're not allowed to. And this is basically exactly what took us to test this application. So with 5 minutes, we were able to instrument the code, to create the first fuzz tests, and to find the bug. So this is a sort of a representative workflow what we did in this project. Okay, so now we have seen how this looks like. How CI fuzz enables the integration of fuzzing in CI/CD, and so now we see 2 use cases, and now let's move to the second use case, to the third use case, which is and let's meet Bob. He works in an old code base that lacks some unit testing, and this represents a networked application. And that's really big in size. It has few millions lines of code, and some of these components have grown historically, and they have a monolithic design, meaning that it's not easy to test some modules in independence of the other ones while mocking the external communications. And so basically what they do system tests. They run the whole system and try to emulate the real communication with the system. In order to, basically here you have these 2 challenges, is that you don't have unit test, and you have a monolithic design. And in order to set up fuzzing for these kinds of projects, or setting up fuzzing on a system level, we have the exact same workflow. So from the setup to creating the test, instrumenting, fuzzing, report, and fixing the bugs. And the only difference here in this case lies on how you create the fuzz test. All remaining steps are identical. And we'll see how this blocks in action. How can we create sort of a system level fuzzy set up system level fuzzing for these kinds of applications. So let me open the third application, which is LightTBD, which is sort of a web server for embedded devices, and it should be should be efficient. And this is one of the applications that we actually tested and found lots of bugs. And so we said the only difference is in the creation of fuzz tests. So what can I do here now is okay, so I want to create a fuzz test. Here you see the types of fuzz tests that we support. And since it's a C++ project, I'm in here, and it's a network application, I can select here, I want to create a network fuzzer. And here, basically, this step was complete. We automated this step in a way, in a sense that you can, with only few configurations, you can generate the fuzz test. And here you don't have to write any code, basically. So all that you have to do is to select the server application, so the server executable, and what type of socket you're targeting, so TCP, UDP, or CAN bus. So CAN bus is really interesting for automotive software, and in this case, it's a TCP application, so you can provide the port number, and you can also select which protocol this application speaks. This would enable the fuzzer to automatically generate sort of valid packets for this application, and do this in a stateful way by sending, like, immutating valid communications for this protocol. And if the application needs some special run and build commands, you can provide it here. And this is all that you have to do in order to create a fuzz test for network applications. You don't have to write any piece of code. So then here we saw how this step is automated. And with this, Max was happy, glad that he integrated fuzzing into its development process, and Bob was also glad that he was able to provide fuzzing on a system level. And actually, the net effect of that is that you have with fuzzing, you have more suitable, stable and secure software, while you save both time and money. And this might trigger a question. So we saw that you can apply fuzzing on a unit or a module level, or similar to the unit test, or on a system level. So one question might be which one you should do in your application, so in an automotive application. So should you do system level fuzzing, or should you do module level fuzzing? Well, simply you need to do both. So with module level fuzzing, you're guaranteeing that when you're testing a module independently of the remaining system, and making sure that it doesn't contain any bugs, this makes it secure for when it's used in the future in unforeseen circumstances. And we've seen several cases where like a module contains some bugs, but these bugs could not be triggered from the outside, but some changes to the system or to the architecture made this the bugs that this module has suddenly exploitable. And so with defensive programming, you'd like to have the modules secure by themselves in order to guarantee the security also in the future. And with system level fuzzing, you test also the interaction between these different modules. And so as a conclusion, in this talk and in Sergey's talk, we saw that fuzzing is superior for bug finding. So it's currently the best or the most effective way to find bugs, and is as a consequence is key for having a secure software. And with CI Fuzz, we do our best to enable companies and developers to easily integrate fuzzing into their development process. And with that, I come to the end of my talk and presentation, and we'll be glad to take any questions if you have.